Well, hello everybody. I'm Roberto Parra. I'm the leader of bioproduction system in sustainable manufacturing. It's a part of a strategic project of the Institute of Advanced Materials for Sustainable Manufacturing. I'm very proud to be part of this great institute. And my pleasure now is to present the next section in which we are going to dive into the exciting work. We continue, of course, of additive innovation. And we, with our esteemed speaker, which is right here, Daniel Frydryk. Daniel is a senior engineering manager specialized in material application and behavior engineering at GE Additives. He will share the insight in the conference of the topic of 3 additive innovations to watch. Thank you, Daniel. Please, the floor is yours.
I have some offloading to do first. All right, first of all, thank you, and I appreciate the invitation to speak today. What I would like to do is actually address some of the things that Matt had just mentioned and kind of build upon them. Because of his expertise and the experience that their organization has in metal additive, that's also where GE is. If you had the opportunity yesterday at Pitt to see the inauguration, the ribbon cutting, that took place in front of GE Additive equipment. So what I'd like to do today is just kind of walk through, first of all, how adorable my dog is. Like, that's just insane. But just talk about where GE is in space and what we're doing with additive technologies. So left to right here, you see the 3 metal additive offerings that GE has. So yesterday, you saw an M2 on the shop floor, as well as its auxiliary equipment that went along with the DMLM, or laser powder bed fusion style technique. We also offer electron beam melting. You'll hear me call it EBM or EBPBF in some instances. The physics are very similar to that of laser, which got talked about a fair deal today, but the energy carriers is not photons in the situations, it happens to be electrons. Finally, on the right-hand side is a binder jet machine. So this closes out our suite of 3 additive modalities. And binder jet, I heard mentioned a couple of times, specifically with the NEMAC panel that was up here. This is really to replace castings. We're at parts at scale, many, many thousands of parts a week, not a year. One of the things that I find most rewarding about my job is that I get to work on all 3 of these with any customer who walks in the door. So there are certainly additive machine OEMs out there who offer 1, maybe 1.5 of these. So when you come in to partner with GE, what you get is an unbiased opinion of which of these modalities is the most likely to prove successful for your particular components. Something else Matt mentioned in the middle of his talk was a fuel nozzle. So the fuel nozzle is really what got GE into additive to begin with. Probably have heard this story before, so I'll keep it relatively brief. But the engineers who were tasked to make a lean-burning fuel nozzle, lean-burning engine, went about trying to find new methods to make a lean burn engine. They produced some of these components to test on rigs. Essentially, it was rapid prototyping to make rig-style tests. When they eventually determined that this is the only way that I can possibly get a part that does what I need it to do, they spooled up and really went after additive in a big way. It's interesting, it doesn't say it on here, this part is actually made of cobalt chrome moly, which is, if anyone's in the medical space, you say, it's a medical alloy, why the heck is it in an airplane engine? The reason is history, pedigree, and data. When going through the FAA certification of this component, it was crucial to have the data necessary to make the regulators convinced that the properties of this component made the part safe. So is this an aerospace material? It wasn't, but it is now. Despite the fact that this isn't a critical application, there's no kinetic energy behind it, there have been 90,000 parts of these produced. There's 28 million flight hours on this component. And if you took an A320neo in the past couple of years, a 737 MAX, or it's the future engine for the Comac C919, you will have additive produced fuel nozzles combust, like right in front of the combustor, making the plane go forward. So despite not being the classic definition of critical, I would argue that there's maybe not a more critical component than the thing that makes the fuel go boom inside of the aircraft engine. A quick example of something that happens in the EBM space is the generation of medical devices. I talked to a couple of people about med devices here. Something very cool that Lima, a customer of GE Additives, is doing is partnering with a business called the Hospital for Special Surgery. It's in New York State. In the same building, you can have your imaging done, CT, MRI, a model made of the trauma location that needs to be repaired, printed, post-processed, and installed in your body. So that is not a regulated device because it's patient matched, it's patient specific, but the whole process is regulated from A to B, A to Z. So as long as you understand what the powder is, the parameter set that you've utilized, the post-processing techniques, you can have a med device that's patient matched or custom to an individual person. And the last one that I want to mention is another EBM part, but it is in the engine, and it does have kinetic energy behind it. This part rotates. This is made of titanium aluminide, which is an intermetallic material at room temperature, something like 0.5% ductility. It is a low-pressure turbine blade, so it sits after the combustor, so I have very hot gases passing by this. But if you've been listening carefully, I've said the word titanium and aluminum next to each other. I took a relatively low, capable temperature-wise material in titanium, added aluminum to it, which is even lower, and somehow I have a rotating part come out the back end. Because this material is an intermetallic, it retains its order through very high temperatures, so you don't have a phase transformation like Ti-6-4 might. But when you try to make this conventionally through a spin casting technique, you get lots of cold shuts and the yield is quite low. But electron beam processes in a high temperature atmosphere, so you can do a lot of welding of these traditionally very hard to weld materials. So I promised you 3 things to watch, and they're all 3 things related to GE. So the first one I want to mention is point melt. So we'll start with EBM, just like those hip cups, as well as those the LPT blades. A quick conversation about EBM. People are generally less familiar with EBM than laser. It's a smaller player in the space. There are no moving parts in the beam column for EBM. Because we don't have photons to move around, you're classically moving those with lasers. I'm using 3 electromagnetic lenses to move those from point A to point B. This beam moves at 8,000 meters per second to get from one location to another. We're also processing in an inert atmosphere that is not gas-based, it's vacuum. We pump a hard vacuum. You end up losing energy and you get backscatter from electrons running into air particles, so we remove those from the equation. And the final one that's worth mentioning is beam power here. These beams are between 4.5 and 6 kilowatts of power, and because of that reason, you can actually penetrate further into the powder bed than you would with a laser beam. To that end, we can use a larger particle size distribution, and therefore the powder is safer. Our titanium powder is not a combustible dust, nor is it a flammable solid because of its size. So here's a couple of videos, and I hadn't seen a video today, so I was a little nervous about this. On the left-hand side is the classic line-style melting. You can think about this as a coloring book. You've handed your kid a book. They're going to draw the outline first and then go scribble on the insides. That's line melting. Point melting, which you see on the right-hand side, has been around for a handful of years. In fact, it's how EBM does its contours, which it's doing right now. But recently, we've gone through a level of effort to industrialize this to make the whole component out of points. Why on earth would we do that? Oh, sorry, an example first. If you're familiar with line-based melting, here's an example of the point-style melting, where in the green dots, it's kind of the bulk region, the light blue dots contour pass, and the dark blue dots would be your actual CAD model exterior. Interestingly, you've seen like DMLM or laser models where you're drawing the contour and then filling in. You're doing one of those and then the other. Because this is point-style melting, you can hop between those locations, and it doesn't matter which portion of the part you're exposing. All of them are fair game at any given time, which gives us a productivity boost. One of the reasons we might want to proceed down a point melt path is tailored microstructure. So what you're seeing on the left-hand side is a nickel superalloy called MARM-247. And on the left microstructure, it's equiax. Kind of hard to tell with the resolution of the picture and the PowerPoint here, but you have equiax structure. In the middle, what amounts to directionally solidified structure. So by changing how those points are behaving when they interact with the powder bed, we can create what amounts to a directionally solidified structure. And the one on the right-hand side is a hybrid version of that. If you were in the turbine blade space, I would imagine you would love an equiaxed root, an equiaxed like top panel, and the portion of the airfoil that you don't want to creep, you could be in directionally solidified structures. So without even changing the powder, you're just slicing the part into slightly different parameters, you can get this hybrid structure that can be utilized for components. On the right-hand side is a Larson-Miller plot. If you're familiar at all with creep, this means something to you. But the point of this plot is to say that we in the EBM space have achieved entitlement. We've matched the performance, of a directionally solidified conventional structure. So additive, there's always been, is this worse? Is this better? Where are we? Here's proof that we have full buy-in to directionally solidified structures. Point melt can also do some cool things with supports and surface roughness. So those are the two that are back to back. And I have some toys to show, and you obviously won't be able to see them from there, but I will be around during lunch and can show you. But a couple of examples of components that are much smoother than you would expect from electron beam components. And you'll notice the roughness plot on the right-hand side over here. The laser powder bed fusion, the blue curve, actually ends at 30 degrees of orientation from horizontal, and the electron beam one progresses. That's intentional. We know how to, in laser space, print really low angles, and it involves slowing the machine way, way, way down to the point of not being productive anymore. I've made my business case even worse. With the electron beam technology and this new point melt, I can actually print pure supportless and have no need for those mechanical supports to a build plate whatsoever. So the reason that you need supports is shown in the upper right-hand side with line melting. So if you have a line and it's actually pushing across that powder bed, I'm making a plow of powder. I'm physically moving the powder with the energy source. Because now I don't have a vector involved, my only direction of energy is down, I don't actually need those supports to tie that part into the powder bed. So on the left-hand side is call it a fiducial. It's made to match kind of this location of the knee implant that I'm holding. And so the point melt on the right-hand side shows a whole lot of green and unfortunately no scale bar. But the comparison on the left-hand side to the one that was measured or created classic line melting with no supports. So both supportless, line melt on the left, point melt on the right. And then finally, point melt can help in a business case scenario. The classic approach for supports in electron beam, because we can nest in space, not everything needs to touch the actual start plate itself. Where we need to remove those supports, they're usually 20 millimeters long or so. You can break them off with a pair of pliers and maybe some tweezers. By hand, essentially, you can do this. But it takes labor. Somebody needs to come and actually do the breaking of those components. If I can print a component that's totally supportless, the part gets turned around a lot faster, and my parts, I'm not paying for that labor, and therefore your business case for these components actually is increased. It's more beneficial to go down an additive path. I would like to just call the orientation out. This part that's shown on the screen right there was built with the little pegs that you can see here facing down. And again, resolution-wise, it's not great, so please make your way up later if you would like to feel the part. But that face with the pegs facing up was actually facing down. So if you're at all familiar with metal additive, you say, holy cow, like it's a game change if you can execute that level of surface roughness on a down-facing surface. Okay, move into topic number 2, which is laser powder bed stitching. Since day one, since laser powder bed has existed, we've always been asked to go bigger and go faster. Really, there's one obvious way to do that, and that's just to throw more lasers at the machine. There are lasers on the market today, there are machines on the market today with 12 lasers on them. I'm sure they have their space, but the regulated applications where understanding where each of those stitch areas and how those perform might not be the right application. The M line is a GE Additive machine that's a 500 millimeter on the side box and 400 millimeters tall, and has 4 lasers on it. So I just want to address where the kind of stitch layout went. A kind of interesting way to go about thinking about stitching is how many different combinations of stitch could you do? If I have my bottom left hand, this is a overlap strategy. I have a laser that sees the kind of peach. I have a laser that sees the pink. I have a laser that sees the blue, and I have one that sees the green. Where would you put a component? Like smack in the middle? Well, maybe. Right in the middle, you can actually see there's overlap of 4 lasers. Would I like to have 4 lasers playing in that space, or do I want to be more specific about what's going on in specific locations? So take this very generic looking part that I've thrown up there. Does it make sense to leave that there, where we know that there's a handful of overlap, or might I want to shift it into a single laser space? It totally depends on the criticality of the component. I can use this machine to make 1 part with 1 laser. But what happens with my productivity? It goes way down. I have 3 lasers just sitting idle on the sidelines doing absolutely nothing. So in general, you'd do something like you see on the right-hand side, which is take a look at a standard laser allocation. But even in this scenario, the upper right-hand corner, the blue one and the peach one, seem to be doing less of this part than the green and the black. So we can take a different look at load balancing. So what happens on the right-hand side is a new kind of method to decide what is going to which laser, and for a couple of reasons, more than a couple of reasons, but the 2 main ones are business case and location or criticality of the component. So this picture on the right-hand side is load balanced. Every laser stays on for exactly the same amount of time. But at the same time, what I've done is I've gone through and made sure that if there are any locations which FEA or FEM might have told me were susceptible to fatigue, are made with 1 laser. So despite the fact that this component has stitches in it, it's in places where my model says, that's okay. That's not a region that I'm terribly concerned about when it comes to the kind of life and livelihood of that component. Before we page away, I do want to take an opportunity to point out some of the kind of odd-looking cylindrical shapes that's at the intersections of those locations. We find it crucial to continue to check the performance of the stitching as an ongoing activity. 1 time on 1 machine with 1 parameter set just simply isn't enough to be an assessment of the health of a stitch line. So in every build that occurs on an M line, the advice, the advocation that we do is to say, go actually measure and pull something from that stitch area. Go check. And there are a number of different things that we can check for. When we get into actually understanding what to go looking for, we need to understand the difference between what the machine is capable of and what the material or the part allows. So we're going to do, in the next handful of slides, take a deeper look at that layout one with the same kind of Tetris blocks that are in there, and there's arrows indicating that each one of those could be shifted with respect to a different one. The shift types in the studies that we've done are mostly shown in the cartoon in the lower left-hand corner, but we investigated and interrogated 2 different types of shift. So you have shear, which is shown on the portion of the left-hand side. So laser 1 and laser 2 are not aligned kind of with respect to a same central location of a circle. But you also have overlap, where those lasers are going too far into one another, and offset, where they're not going near enough to one another. So all of the investigations and optimizing of a parameter set that exist for M-line stitching took into account, I think it's 5 specific measures of the non-matching nature. So it's pure shear, it's pure offset, pure overlap, and then shear offset, shear overlap. So you cannot have misalignment happen in any other fashion besides those. To investigate, we went through and actually checked different measures, what we were calling countermeasures. So what are you actually doing to the component what are you doing to the parameter set to make sure that the component is okay? So one that you're seeing over here is a combination of overlap, so you're just intentionally making those vectors ride into one another, as well as what we call tail tucking. So the parameters come across each other and then they dive back into the bulk portion of the part as the actual component is created. So you can see the difference between the one with no countermeasures applied whatsoever on the left-hand side and the one on the right-hand side which does have countermeasures applied. So essentially with those measures in place, the contour discontinuities, because of those multi-laser setup and the intentional stitching, were removed with this new model of machine. How do we prove this to ourselves? What you're looking at on the left-hand side here is a stack of horizontal tensile bars. Now, it have to be horizontal because if we stitch a vertical tensile bar, it's going along the direction of the applied tensile stress. So it's probably not going to tell us all that much. So our main measure of success here for just general bulk understanding of success or not is horizontal tensile coupons. So we've put together a series of box plots where on the left-hand side of every box plot or every graph is the stitched version, and on the right-hand side is unstitched or bulk material. Without running statistics, and they'd be quite easy to run, we can show that we can just visually see that these 192 specimens that were tested in nickel 718 show really similar behavior between the stitched and the unstitched regions. But what I just showed you on the prior slide was, it seems to be a surface issue and not a bulk issue, and I don't see a gauge section in here. So the next logical step is to say, I've machined away the area that I most care about, which is what's happening on the surface. Surfaces tend to be the location for initiation of failure in fatigue applications. So to fix that, we went through and tested coupons with as-printed surfaces on them. So this was a shear overlap style investigation, so those types of offsets that we had mentioned, types of mismatch that we had mentioned. This is a shear overlap. And we printed with a single laser what you're seeing in the red. They're horizontal horizontal fatigue specimens. You can get that stitch right down the center of it, and you're leaving the surface intact. So what we were missing from tensile before, we are now adding. Fatigue is also the first one that's going to pick up on any flaw because of the crack propagation that takes place when you have fatigue specimens. So when you look at this plot of two different stress levels, you can see how similar the stitched and the unstitched samples are when you apply the correct type of countermeasures and control the parameter set. So I think for the first time in stitching and laser history, it can be said that there's no statistical difference between a stitched location and an unstitched location, which allows us to be very aggressive with the placement of parts and the strategies for slicing. Now, we no longer need to take a debit. We no longer need to be turning our debit to build time. We no longer need to be taking our lasers offline, so the load balancing ends up being more similar. The last one I wanted to address in our 12 minutes that's remaining is the definition of scale when it comes to binder jet. So as I promised, the mandate with additive is go faster and go bigger. Go bigger is easy to do on binder jet, relatively speaking, because of the fact that every pass, the exposure area is capable of being kind of dropped onto. And if you're unfamiliar with binder jet, think about like an inkjet printer that's dropping glue onto metal powder. You don't have a point-based energy source to go draw a line and color it in. You have a series of print heads that just sweeps from left to right. And so if I'm building one tiny little straw and its full Z height, or I'm building the full available cross-sectional area, it takes the same amount of time. So in theory, a large part is pretty straightforward. It's not all that complicated to produce. But in terms of scale for quantity, can you actually use all of the available space that we have? We've made some strides there as well. So if you're less familiar with binder jet than you are with the laser process or even electron beam, just a quick layout of the methodology to go through and create a part. it is certainly the most complicated set of post-processing of all of the additive techniques. They come out in what we call a green state, so it's just powder that's glued together, and it needs to be subjected to a sinter cycle. Up to 80–90% of the melting temperature, that lets the kinetics take over, and then you have motions, atomic motion across the surface of powder particles, and you get shrinkage on the order of 20 to 30% on a linear basis across a component. So in BinderJet, it's easy to say we can print anything. Like, it's really easy to print stuff in BinderJet. You can get, with 600 or 900 dots per inch on the print heads, you can resolve a lot of components. The question is, do those thin walls or that structure, does it survive through the sinter cycle? So that's why we spend a lot of time optimizing our debind and sinter with the proprietary binder system that belongs to GE. How do we get to huge quantities of parts and large parts? The answer to this is the BinderJet line series 3. And so one of those kind of kits of equipment contains obviously the printer. It's the engine of the structure. And you have two handling stations, one for binder and one for powder, because consider so far we've only had one feedstock to worry about. It's been just powder as it enters the laser system, or just powder as it enters the electron beam system. Now we also have binder to worry about and how to handle that as well. So those are our two accessories. And on the right-hand side of this screen here is the depowder station. Still a relatively manual process because no two builds are quite the same for our customers just yet. The goal of binder development is to give those parts such green strength that you could automate this process, pick them manually, and depowder. That's only successful, one, with a high-strength binder, but on top of that, serial production, so that you're not reprogramming the depowdering cycle every single time. It is worth mentioning some of the automation that can be incorporated or utilized by this piece of equipment, because this goes with the quantity of parts. So the automation is shown here on this plot, kind of flow chart of what's happening in the BinderJet system by solid lines. So anytime on this chart you're seeing a solid line, this happens without manual operation, and there's no touching the machine. It just is called by the logic, and then it's either asking for instance, binder from the material handling station binder, or it's asking for powder from the MHS powder, all totally hands-free. There are a couple of locations where we do not automate it, and there's never a goal to automate that, and it's things like the build box handling. This machine is made to go into things like tier 1 automotive manufacturers, where I don't profess to know the methodology that they choose to use to grab the box and move it from one location to another. So this is automation ready, but not currently automated, just because those solutions are so customer specific. But as soon as someone reports back, a customer says, I'm interested in adding this type of automation in there, that stub conveyor that you can see sticking off the front can disappear, or you could make it longer. There's all sorts of these knobs that can be turned to make parts at scale in terms of quantity. In terms of large parts, I missed one thing, apologies. I wanted to talk about the AMP software, which is on the left-hand side of this screen. BinderJet is notoriously tricky for not making the part come out of the furnace like it did when it went in. And to drive that home, I have two motorcycle manifolds that my colleague designed. And probably hard to tell from where you're sitting, but again, please come up and get them later. He designed the part the first time and applied the right scaling factor, just based on linear scale. We know it shrinks, call it 24%, whatever the actual number is. So scaled it up, put it in the sinter furnace, and just let what happens happen. So I think it's probably easy enough to see is that these legs splayed out. There was a body load that actually caused these legs to splay out. Oh, yes, perfect. So these legs have splayed out, and then on top of that, this top flange here has kind of gone into potato chip mode. So this was no attempt at compensating the part before it went in the furnace. The second one I have was run through AMP, which is built on GE data as we're developing these sinter cycles. And so you can see that these legs are no longer splayed out and that this top flange is nice and flat. So part of the reason to use AMP is to make those very large scale components. And we can head back to the slide deck if you would. Thank you. So using that AMP software to go and scale those large components, because as they get bigger and bigger, and that's heavier and both size-wise, they get less and less predictable in the furnace. So any effort we can do to go through and actually optimize based on predictions and some modeling data that we have and we've collected gives us a better attempt at counteracting the forces of friction and that of body load. It just wants to sag on its own. Okay. On the right-hand side of the screen, I want to show you two things that I'm allowed to show you, because there's a component that belongs to a customer that's, I think, 22 kilograms in mass. So if you're American, you want to talk pounds, but 22 kilograms in mass that is perfectly well sintered, and its thickest cross-section at 3 centimeters is dense from edge to edge. And this is because of the sinter cycle that's applied, as well as that AMP compensation software, and the very consistent powder bed density that we have when the part is actually printed. But the two that are kind of sizable that we take to trade shows are on the right-hand side of this slide here. So the one on the left, I have the number. The one on the left is 350 millimeters in diameter, and the one on the right is 275. And these also went through the AMP software, and you can actually tell that if you kind of peek in I suppose that's like a 730 position of the left hand, the gap in that part. You can actually see some of the intentional kind of ridge or layer lines that are left over because of the compensation that was applied to the component. Additionally, all of those kind of overhangs, they're not sagged down, which tells me when we printed the part, they were arched up. So there's some very basic things that were implemented into AMP, but also some that were quite data-based and many, many numbers of DOEs and measurements taken. On the bottom side of this, you can see that manifold that I had held up earlier as the AMP example. And what's kind of maybe the takeaway from this one is that we didn't design this for trade shows. We designed this because a colleague of mine needed a new manifold for his Honda motorcycle. And we didn't expect it to fit the first time, and turns out we needed to compensate it. But after the fact, it fit right on. So after printing and after sintering, we get to, if you're familiar with sand casting, CT7 and CT9 levels of fidelity, of tolerance on these components. So as promised, a binder jet replacement of castings, the tolerances are already there. The last thing that we want to address in the handful of minutes we have is the most common question we get about binder jet is, can I use the full build chamber? Simple answer, yep, sure can. This, though, is pretty tricky when you think about how can I possibly, at full build in 316 stainless or any of the steels, I'm trying to move 650 kilograms, 100 microns at a time. And if I can't do that, if I'm at 125 microns of step, now my binder kinetics, my wicking, my temperature profile, all of those things are not as they were designed to be. So the methods to utilize the full build volume only come around from robust and rigorous front-end engineering. We control the temperature of the powder. We control the viscosity of the binder. We have a very robust Z-stage control. So can you use the full build volume? Yes. Can I make large parts? Yes. Can I make medium-sized parts that use the full build volume? Absolutely. The beauty about the binder jet technology is, in similar style to electron beam, I can nest in Z-space and nothing has to touch the start plate. So this is really, really geared towards massive, massive quantities of components for our friends in the kind of automotive industry. And the the types and availability of tolerances. You can see a Conrod, for instance, and layout of Schroy's manifold there as well. The types of parts you can build are limitless. The question of because you can, should you, still applies in binder jet, but instead of can you do the binder jetting, here it's more of a can you sinter it, because that's the struggle with our binder jet components and anybody's binder jet components. I don't know if anybody happens to be going to Formnext, but GE will have a presence at Formnext if you want to meet at the booth and ask any questions. I think we put the, Hall 11, booth D41. We'll have representatives there who can mention any of our modalities, including the powder production business. So AP&C, which belongs to GE, is a leader in titanium production, and they'll have people there to address any additional questions you might have or ones that I might not be able to answer today. All right, thank you.
Thank you very much, Daniel. Very enlightening talk, and I think this is the time for all the questions. Please have a seat, please. Questions here? Dr. Elias.
Thank you, Daniel, for your talk. I saw that technology two years ago.
The binder jet?
We were in Detroit. We were discussing about the possibility of having that here in Mexico. I believe that it has a lot of potential, as you mentioned, to move into mass production and so on. Yep. But just for the general public, I would like to ask you a question, and maybe you can address that. Regarding the end properties of the product, what are your thoughts about that? It is reliable. For instance, we have already saw some talks about fracture cracks and so on, reliability, repetitivity. What are your thoughts about that, about this technology, and what is the coming future and promise coming from this technology?
Yeah, good questions. We have data sets that today show properties that are equivalent to cast properties, and those are against normal kind of industry standards. So what we found is that the automotive industry is doing less generation of their own material properties and are just attempting to meet a standard that exists. They don't want to carry material data cards, which I don't blame them for. So the mandate when we go through a new development program to put a new alloy on this piece of machinery is to meet the current existing casting standards. We're already asking our customers to make an enormous shift from a conventional manufacturing methodology to a brand new one. So one of my mandates as a materials engineer is to make sure that the properties that we are getting out of that machine are no worse than that of the incumbent technology. So for the data sets that we have, we've shown that the cast properties are right in the same ballpark as ours. And as we look forward to the future, which is the second half of your question, it's not end properties, but for me, it's green strength. So how much can we increase the strength of just that powder glue, powder ink combination? Because as that gets stronger and stronger and stronger, we can build bigger and bigger components that aren't going to collapse under their own body weight, and we can introduce automation into the systems. I mean, you just look at what's happening in your neighborhoods with the increase of production and manufacturing here. That's going to be some degree of automation, and there's machinery involved. We see the writing on the wall there too, and therefore would go through every effort to make sure that machines can interface with those green parts to take the labor portion out, to make it quicker, to make that business case a whole lot better. So I think both halves of your answers are strength. We can meet the ASTM standards and other standards that are asked of us, but on top of that, green strength is the future.
Thank you very much.
Thank you.
Hello.
Hi.
My name is Aitzol Amikit from the University of the Basque Country in Spain. And first of all, thank you for your presentation. I think that has been very interesting. And my question is related with binder jetting technology, and more specifically in the application of binder jetting for aerospace parts.
Sure.
and basically difficult to weld aerospace parts such as M247. So how do you see in the present and in the future because of the porosity issues and, you know?
Sure. It might not surprise you if you're familiar with General Electric at all that the binder jet has been in our pipeline for a long time. The laser company that part of GE now and the electron beam company were inorganically acquired. We went out and bought those businesses. Binder jet we grew totally from the ground up at our facilities in Cincinnati, Ohio, as with help from the Global Research Center in New York. And you ask, why was the Global Research Center involved? For superalloys. So to what degree can you get away with, with nickel applications for binder jet? And it should hearten you to learn that the very first alloy we ever put on a machine was a nickel superalloy. So can we print those? Yes, can continue to do that. The question is what comes during the sinter cycle. So if you have a big gap between your solidus and your liquidus lines and you can just kind of touch the edge and not precipitate carbides and grain boundaries and some of those things, we have certainly the availability and the capability to use those alloys in binder jet. Like I mentioned when I was kind of up by the podium, the most difficult part about binder jet is the sintering cycle. And if you create a structure during the sinter process, is there any method via heat treat to undo it? Can you put things back into solution, or were those phases created at such high temperature that you would need to go back up there and quench again to put them back into solution? So to kind of roundly answer your question, our history with binder jet is based on superalloys. And the difficulty with those superalloys always lies in the subsequent heat treatment.
Thank you. Thank you very much.
Thank you. Daniel, we have a question from the audience. So they are asking this for you. They say, I know that using this type of additive manufacturing with metal could have a little imperfections. So holes and things like that. Is that true?
Sure. So I would guess that the asker is curious about porosity, and we do notice porosity in these components. The good news is that we have gone through and characterized those parts with the porosity inside of it. So my example that I just gave about meeting ASTM standards, should there be any porosity in those samples, it's reflected in the properties of our components. So even in aerospace, you saw the fuel nozzle, you saw the titanium aluminide blade, those either were generated, they had porosity in them and they were hipped away, or they have residual porosity left over because it was not put through a hot isostatic press process. When we made the material curve, so fatigue or tensile at temperature, it accounts for the presence of those small voids in the material. So even if they do exist, we have the data to show that the application of that alloy in that modality should be perfectly fine for that component. I'll add something I didn't mention when we talked about EBM is that one of the benefits of electron beam is that those voids are literally full of nothing. Because the chamber was pumped to vacuum when we started the process, the voids, should they exist, have nothing inside of them. So when you go through and you put those through a hot isostatic press process, those pores close up very, very nicely. There is some research out there with the laser powder bed fusion techniques, which are processed typically with nitrogen or with argon, that if you close those pores during a hot isostatic press, but then you raise that component up, it has a high service temperature for its life, that inert gas, which was previously trapped in the matrix of the kind of metal atoms, comes back together and you form pores again. So there's a benefit sometimes of running in electron beam technology, because when you hip, it's permanent. Sometimes high temperature laser product, those pores can re-evolve and they may exist again in your components.
Excellent, thank you. Probably we have just 2 minutes for last question. Yes.
The roughness of the material. How do you measure the roughness of the material?
Sure, we use 2 methods, and they're the methods you are familiar with. So one is tactile profilometry. So you're just scraping a 10 micron kind of radius tip across the part. But on top of that, we'll use like a laser confocal microscope or similar to measure. The thing we warn our customers about is to not mix those two measurement methods, because the additive surface roughness has valleys that the stylus type cannot just get into. It's impossible for it to get down there. So almost without exception, you'll have a rougher surface from the optical measurement methods than you will with the kind of tactile methods where you're just moving across. It is imperative, though, because as we've claimed with kind of the knee, is that we measure roughness everywhere, because we have sidewall roughness, we have top roughness, we have overhanging angle roughness. So if you were to see a build layout, the last build we ever do before we issue a parameter set, it has roughness coupons in kind of a clever way, is that, you know, if I have one over here measuring, call it 45, I got my down skin and my up skin, and that's when my laser is coming at a, you know, a almost normal incidence angle. But I could move it all the way over here, and now my angle of my laser is skipping off the surface of that. So when we report surface roughness, it's everywhere. And so that's both orientation-wise and location on the platform, because the process does kind of dictate that we do check those things.
Thank you everybody for this section, and thank you, Daniel. Thank you very much. Excellent presentation. We're really thrilled with your knowledge. Thank you. Hold on.